In today's hyper-connected world, the demand for semiconductors, the tiny chips powering everything from smartphones to cars, is exploding. Yet few outside the tech industry realize that a single company plays a pivotal role in making the most advanced microchips possible. That company is ASML, a Dutch tech giant whose machines are the unsung heroes behind nearly every modern chip. ASML's story is one of innovation, ambition, and navigating a fiercely competitive global industry. Unlike chipmakers like Intel or Samsung, ASML doesn't manufacture chips itself. Instead, it designs and builds the extraordinarily complex lithography machines that etch microscopic patterns onto silicon wafers, the crucial first step in chip production. Without ASML's machines, the semiconductor industry would be stuck at a technological standstill. Founded in 1984 as a joint venture among Philips and other Dutch companies, ASML began as a modest player in a field dominated by giants from the US, Japan, and later South Korea. But through decades of relentless research and bold technological leaps, ASML transformed into the indispensable backbone of the global semiconductor supply chain. Its machines, especially those using extreme ultraviolet (EUV) technology, are the most advanced and precise ever built. This story isn't just about technology. It's about geopolitics, trade wars, global supply chains, and the quiet yet intense race to control the future of computing. It's about the tiny imperfections measured in nanometers that can make or break a chip's performance. And it's about a company that, against the odds, became a linchpin in the digital age. In the coming parts, we will explore how ASML grew from a niche European startup into a global titan, the science behind its revolutionary machines, the challenges it faced in a fiercely competitive market, and the critical role it plays in shaping the technology that defines modern life. The story of ASML begins in the early 1980s, a time when the semiconductor industry was dominated by a few major players, particularly from the United States and Japan. The process of creating microchips relied heavily on photolithography, the technique of projecting light through masks onto silicon wafers to etch circuit patterns. This process required extremely precise machinery, but the technology was mostly controlled by established companies such as Nikon and Canon from Japan, and several American firms. In the Netherlands, Philips, a global electronics giant, had been involved in semiconductor manufacturing for years but was still dependent on external suppliers for photolithography equipment. Recognizing the strategic importance of mastering this technology, Philips joined forces with the Dutch machine tool manufacturer ASMI and another Dutch company to form a joint venture in 1984. This new company was named ASML, standing for Advanced Semiconductor Materials Lithography. ASML's initial goal was ambitious but clear: to develop and produce lithography machines that could compete with Japanese and American equipment, and eventually push the boundaries of what was technologically possible. This was no small task. The machinery needed to project extremely detailed images at nanometer scales, requiring breakthroughs in optics, mechanics, and control systems. In its early years, ASML faced enormous challenges. The company had limited experience compared to industry giants and had to innovate quickly to survive. The team focused on developing step-and-repeat cameras, a type of lithography system that allowed wafers to be exposed piece by piece, improving precision and throughput. Early models were bulky and complex, and production volumes were low, but the groundwork was being laid. ASML's approach was methodical. The company invested heavily in research and development, hiring engineers and scientists with expertise in optics, physics, and materials science. Collaborations with universities and research institutes in Europe helped build a knowledge base that would prove invaluable in the decades to come. A turning point came in the late 1980s and early 1990s when ASML began shipping its first commercially viable lithography machines. Although these early models didn't immediately displace Japanese competitors, they established ASML as a credible player in the market. The company's machines were praised for their innovative designs and precision, attracting attention from semiconductor manufacturers eager for alternatives. At the same time, ASML expanded its manufacturing capabilities and improved its supply chain, enabling higher production volumes. The company also cultivated strong relationships with key chipmakers, which provided valuable feedback to refine the machines and tailor them to evolving industry needs. By the mid-1990s, ASML was gaining momentum. The company introduced new generations of lithography systems with improved resolution and speed, steadily closing the gap with established competitors. It became clear that ASML's commitment to innovation and quality was paying off. Despite the progress, the road ahead remained steep. The semiconductor industry was rapidly evolving, with chipmakers pushing for smaller, faster, and more energy-efficient transistors. To stay relevant, ASML would need to pioneer entirely new technologies, an effort that would define its future. The early years of ASML were marked by perseverance, vision, and a commitment to mastering one of the most complex manufacturing challenges in the world. This foundation set the stage for the company's transformation from a niche European player to a global leader in semiconductor technology. As the semiconductor industry advanced through the 1990s and early 2000s, the relentless pursuit of Moore's Law, the principle that the number of transistors on a chip would double approximately every 2 years, pushed lithography technology to its limits. Chipmakers demanded ever finer patterning on silicon wafers, requiring machines capable of projecting images with resolutions measured in nanometers. ASML, already establishing itself as an innovator, faced the enormous challenge of developing the next generation of lithography equipment to meet these demands. At the heart of this challenge was the wavelength of light used in photolithography. Traditional machines operated in the deep ultraviolet (DUV) range, using light with wavelengths around 193 nanometers. While effective for many years, this wavelength was reaching its physical limits as semiconductor features shrank below 100 nanometers. To continue shrinking transistors, a fundamentally new approach was required, moving to much shorter wavelengths. This necessity gave birth to the idea of extreme ultraviolet lithography, or EUV. EUV used light with a wavelength of about 13.5 nanometers, an order of magnitude shorter than DUV. This would allow patterning of far smaller features with higher precision. But the technical hurdles were immense. EUV light is absorbed by almost every material, including air, meaning the entire optical path had to be maintained in a vacuum. Producing EUV light at sufficient intensity and stability required complex plasma sources. Moreover, the mirrors and lenses for EUV machines had to be engineered with extraordinary accuracy. ASML embarked on a long-term research program to develop EUV technology, partnering with companies like Carl Zeiss for advanced optics and leading semiconductor manufacturers like Intel, Samsung, and TSMC who provided funding and collaboration. The EUV project was a high-stakes gamble that demanded billions of euros and years of painstaking engineering. Throughout the 2000s, ASML released successive generations of DUV lithography machines that pushed resolution closer to theoretical limits. Meanwhile, prototypes and early versions of EUV machines were developed and tested. The initial EUV tools were bulky, expensive, and prone to low uptime, making them impractical for mass chip production. However, the progress was steady, and ASML's engineers refined the plasma light sources, mirror coatings, and wafer stages to improve reliability and throughput. During this period, ASML's commitment to EUV set it apart from competitors who were more cautious or focused on incremental improvements to existing technologies. The company bet on EUV as the future of lithography, a bet that would eventually pay off handsomely but required patience and resilience. At the same time, ASML expanded its footprint globally. The company's machines became increasingly popular among leading semiconductor manufacturers eager to maintain their edge in the chip race. The deep collaboration between ASML and its customers led to continuous improvements and innovations, fostering a unique ecosystem centered around the company's lithography platforms. By the late 2010s, ASML was ready to deliver on the promise of EUV. The machines had become smaller, more reliable, and capable of operating at commercial production volumes. The first major chipmakers began deploying EUV lithography in volume production, enabling chips with transistor features measured in single-digit nanometers, technology that powers today's most advanced smartphones, servers, and AI processors. ASML's breakthrough with EUV lithography cemented its position as the indispensable supplier in the semiconductor industry. No other company could match the technological complexity and precision required to build these machines. With a near monopoly on EUV tools, ASML shaped the future of chip manufacturing for years to come. This period of technological breakthrough was marked by vision, collaboration, and the overcoming of seemingly insurmountable engineering challenges. It demonstrated how a company born in the shadow of giants could rise to lead a revolution in one of the world's most critical industries. As ASML's technology matured and its machines became the cornerstone of advanced chip manufacturing, the company found itself at the intersection of global economic power and geopolitics. The semiconductor industry was, and remains, a strategic asset, underpinning everything from consumer electronics to military hardware. This reality thrust ASML into a complex web of international relations, trade policies, and supply chain vulnerabilities. The company's headquarters in the Netherlands placed it squarely within the European Union's regulatory and diplomatic framework. While Europe was not a dominant chip manufacturer compared to the US, South Korea, Taiwan, or China, ASML's role as a supplier of critical technology gave it disproportionate influence. Governments worldwide recognized that access to ASML's lithography machines was essential for any country or company aiming to produce the latest generation of semiconductors. One of the most challenging geopolitical dynamics ASML faced was the rising tension between the United States and China. The U.S. government viewed semiconductor technology as a matter of national security, implementing export controls to restrict China's access to cutting-edge equipment, including EUV lithography machines. These policies directly impacted ASML's sales strategy and relationships, as China represented a massive and growing market for semiconductors. ASML had to carefully navigate these restrictions while maintaining its commitments to customers in other regions. The company complied strictly with export controls, unable to sell its most advanced EUV machines to China. This decision was both a reflection of legal requirements and the broader geopolitical pressures influencing technology trade. Meanwhile, ASML's supply chain was a marvel of global collaboration but also a source of potential risk. Building a single EUV machine involved thousands of components sourced from dozens of suppliers around the world. Precision optics came from German firms, high-tech sensors from the United States, and specialized materials from Asia. Coordinating this complex network required meticulous planning and resilience, especially during global disruptions like the COVID-19 pandemic. The pandemic underscored vulnerabilities in global supply chains and heightened awareness of the semiconductor industry's strategic importance. ASML's machines, essential for chip fabrication, became critical assets not only for consumer electronics but for entire economies. Governments increased their investments in semiconductor capacity, often citing ASML technology as a prerequisite for advancing local manufacturing ambitions. In response, ASML expanded its manufacturing and service operations to meet soaring demand. The company invested in new facilities and trained a growing workforce to assemble and maintain its intricate machines. Service technicians were deployed worldwide, ensuring that customers' equipment operated at peak efficiency, a vital factor given the machine's complexity and cost. ASML also engaged with policymakers, industry consortia, and international partners to promote a stable environment for semiconductor innovation and trade. The company's leadership recognized that sustaining technological progress required cooperation across borders, even amid geopolitical tensions. Navigating this geopolitical landscape was a delicate balancing act. ASML's technology was coveted but also scrutinized, with the company caught between competing interests. Its ability to operate successfully depended on maintaining trust, compliance, and agility in a rapidly shifting global environment. The company's role in this high-stakes arena highlighted how technological innovation and international politics were deeply intertwined. ASML was no longer just a supplier of equipment, it had become a strategic player influencing the global balance of power in the digital age. While ASML's lithography machines remained the heart of its business, the company recognized early on that innovation couldn't stop at just building better tools. The semiconductor industry was evolving at a breakneck pace, and ASML's success depended not only on developing groundbreaking hardware but also on creating comprehensive solutions that helped customers push the limits of chip design and production. One key area of innovation was in software and automation. ASML developed sophisticated software platforms that optimized machine performance, improved precision, and increased throughput. These tools allowed chip manufacturers to plan complex lithography processes, simulate patterning outcomes, and monitor equipment health in real time. By integrating hardware and software tightly, ASML offered customers a more efficient and predictable production environment. Moreover, as chips became more complex with multiple layers and diverse materials, lithography alone wasn't enough. ASML expanded its research into complementary technologies, such as metrology and inspection systems. These systems used advanced imaging and sensors to detect defects on wafers at microscopic scales, providing feedback that was essential for maintaining high yields and quality in mass production. Collaboration was another pillar of ASML's innovation strategy. The company worked closely with semiconductor manufacturers, equipment suppliers, and research institutions through partnerships and consortia. Initiatives like the International Technology Roadmap for Semiconductors (ITRS), and later the Joint Development Programs enabled ASML to align its technology development with industry needs, anticipating future challenges and opportunities. A significant innovation milestone was ASML's move into computational lithography. This approach combined hardware, software, and complex algorithms to correct optical distortions and compensate for physical limitations. Computational lithography allowed chipmakers to design patterns that would otherwise be impossible to print accurately, extending the lifespan of existing lithography technologies while preparing the way for EUV adoption. ASML also invested in workforce development and knowledge sharing. The company ran training programs and established research labs to foster expertise in emerging fields like optics, materials science, and nanotechnology. By cultivating talent, ASML ensured it could sustain its innovation momentum in an industry where expertise was a key competitive advantage. Recognizing the growing environmental concerns associated with semiconductor manufacturing, ASML began efforts to improve the energy efficiency and sustainability of its machines. Initiatives included designing equipment with lower power consumption, reducing waste in manufacturing processes, and working with customers to optimize resource use. Innovation extended beyond technology to ASML's business model. The company developed comprehensive service offerings, including maintenance contracts, remote diagnostics, and software updates, creating long-term relationships with customers. These services provided recurring revenue streams and ensured that ASML's equipment remained at the cutting edge throughout its lifecycle. By continually pushing innovation across hardware, software, and services, ASML not only reinforced its position as a lithography leader but also expanded its role as a holistic partner to the semiconductor industry. This approach helped customers navigate the increasing complexity of chip production while preparing ASML for future growth opportunities. In a rapidly changing technological landscape, ASML's commitment to innovation beyond lithography underscored its vision to enable the impossible in chip manufacturing, powering the devices and systems that define modern life. As ASML advanced its technology and broadened its innovation footprint, it also solidified its status as a global leader in the semiconductor equipment market. The company's journey from a European startup to a critical pillar of the international tech ecosystem was marked by strategic growth, expanding customer bases, and deepening influence across continents. By the mid-2010s, ASML had become the only company in the world capable of producing extreme ultraviolet (EUV) lithography machines at scale. This technological exclusivity translated into a near monopoly in the most advanced segment of the lithography market, giving ASML unprecedented leverage and responsibility. Semiconductor manufacturers seeking to produce the latest generation of chips depended almost entirely on ASML's tools. The company's customer portfolio included industry giants like Intel, Samsung, Taiwan Semiconductor Manufacturing Company, TSMC, and SK Hynix. These partnerships were not just transactional but collaborative, with ASML often working closely with customers on co-development projects to tailor lithography systems to specific manufacturing needs. Global demand for semiconductors surged in the 2010s and early 2020s, fueled by the growth of smartphones, data centers, artificial intelligence, automotive electronics, and the Internet of Things. This boom increased the need for advanced chip production capacity, directly benefiting ASML's sales and market position. To meet this demand, ASML expanded its manufacturing facilities, investing heavily in production capacity and workforce development. The company built state-of-the-art assembly plants in the Netherlands and opened new research centers worldwide. Hiring thousands of engineers, technicians, and specialists, ASML grew into a multinational corporation with a presence in Asia, North America, and Europe. ASML's leadership also focused on maintaining a robust supply chain capable of handling the complex and delicate components needed for its machines. The company fostered long-term relationships with suppliers, emphasizing quality, innovation, and resilience. This approach helped mitigate risks from global disruptions and ensured consistent delivery to customers. In addition to expanding production, ASML worked to enhance its customer support and services network. Given the intricacy and cost of EUV machines, often exceeding $150 million each, customers required extensive technical support, maintenance, and training. ASML established regional service centers and deployed highly trained field engineers to provide rapid assistance worldwide, ensuring minimal downtime for chip manufacturers. ASML's market leadership was also strengthened by its intellectual property portfolio. The company invested heavily in patents and proprietary technology, protecting its innovations and maintaining a competitive edge. Its extensive patent holdings covered critical aspects of lithography, optics, software, and system integration, making ASML a formidable player in technology licensing and partnerships. The company's financial performance reflected its growing dominance. Revenues and profits climbed steadily, and ASML became one of Europe's most valuable technology firms, often drawing comparisons to Silicon Valley giants. Its stock attracted global investors interested in the semiconductor supply chain's future. Beyond commercial success, ASML's expanding influence shaped industry standards and practices. The company played a central role in international consortia and forums, helping set technological roadmaps and fostering cooperation among chipmakers, equipment suppliers, and governments. ASML's rise was a testament to its ability to combine cutting-edge innovation with strategic growth and global engagement. By the late 2010s and early 2020s, the company had become not just a supplier but a pivotal force in the semiconductor ecosystem, driving the industry forward and enabling technological advances that touched billions of lives. The ascent of ASML to the forefront of semiconductor technology was not without its share of formidable challenges. The complexity of extreme ultraviolet, EUV, lithography and the rapidly changing geopolitical and economic environment required the company to demonstrate remarkable resilience and adaptability. One of the most persistent challenges was the extraordinary technical complexity of ASML's machines. Each EUV system consisted of hundreds of thousands of components, many of which pushed the boundaries of what was physically possible. The precision required was measured in nanometers, and even the slightest misalignment could lead to defects in chip production. Maintaining high manufacturing yields and consistent machine uptime demanded constant innovation in quality control, assembly processes, and system diagnostics. The development cycle for new lithography tools was lengthy and expensive, often spanning several years. Delays or setbacks could jeopardize relationships with key customers who operated under tight production schedules and fierce competition. ASML's engineering teams had to balance speed with reliability, ensuring that innovations met the stringent demands of the semiconductor industry. Economic downturns and fluctuations in the global semiconductor market also tested ASML's stability. Periods of oversupply or shifting customer priorities occasionally led to reduced orders or postponed equipment purchases. The company navigated these cycles by maintaining financial discipline, diversifying its customer base, and investing prudently in research and development to stay ahead of the curve. Geopolitical tensions added another layer of complexity. Trade restrictions, particularly those involving China and the United States, required ASML to carefully manage export licenses and compliance. The company had to enforce restrictions on sales of its most advanced EUV tools to certain markets, balancing legal obligations with commercial opportunities. These dynamics sometimes strained relationships and added uncertainty to long-term planning. Supply chain disruptions, such as those triggered by the COVID-19 pandemic, posed additional hurdles. ASML's global network of suppliers faced challenges related to shipping delays, material shortages, and workforce constraints. To mitigate these risks, ASML enhanced its supply chain visibility, built strategic inventories, and collaborated closely with partners to ensure continuity. Despite these obstacles, ASML's culture of innovation and problem-solving proved vital. The company fostered a collaborative environment where engineers, scientists, and managers worked together to troubleshoot issues, share knowledge, and accelerate improvements. Continuous learning and agility became cornerstones of ASML's approach to overcoming adversity. ASML also benefited from strong support from its customers and governments. Semiconductor manufacturers valued ASML's commitment and transparency, working alongside the company to address challenges and develop solutions. Governments recognized the strategic importance of ASML's technology, providing funding and policy support to bolster the semiconductor ecosystem. The company's resilience was tested again as the semiconductor industry faced unprecedented demand surges in the early 2020s. Meeting production goals required ramping up capacity without compromising quality, a difficult balancing act under any circumstances. ASML responded by expanding production lines, enhancing workforce training, and deploying advanced automation techniques. ASML's journey through technical, economic, and geopolitical challenges highlights the complexity of operating at the cutting edge of technology. Its ability to adapt, persevere, and innovate ensured not only its survival but its continued leadership in a highly competitive and dynamic industry. As the 2020s unfold, the semiconductor industry stands on the brink of new frontiers that promise to reshape technology, society, and the global economy. ASML, with its unique position as the provider of the world's most advanced lithography equipment, is poised to play a central role in this ongoing transformation. One of the key trends driving the future of chip manufacturing is the push towards ever smaller and more powerful transistors. While extreme ultraviolet (EUV) lithography has enabled feature sizes below 10 nanometers, the industry is already exploring next-generation technologies such as High-NA numerical aperture (EUV), which promises even greater precision and density. ASML is actively developing High-NA EUV machines designed to extend Moore's law further, enabling chips that are faster, more energy efficient, and capable of supporting increasingly complex applications. Beyond shrinking transistor sizes, chip designers are innovating through new architectures and materials. 3D stacking, heterogeneous integration, and novel semiconductor materials like gallium nitride and silicon carbide are opening fresh possibilities for performance and efficiency. These advances create new lithographic challenges and opportunities, which ASML is addressing through collaborative research and tailored solutions. Artificial intelligence, AI, machine learning, and quantum computing represent other transformative frontiers where semiconductor technology plays a foundational role. The demand for specialized chips designed for AI workloads, edge computing, and quantum processors is accelerating. ASML's lithography tools enable manufacturers to produce these highly specialized devices, fueling innovation in fields ranging from healthcare to autonomous vehicles. Sustainability is becoming an increasingly critical consideration. Semiconductor manufacturing is resource-intensive, involving significant energy and water consumption. ASML is investing in environmentally responsible technologies, designing equipment that minimizes waste, reduces power usage, and supports circular economy principles. The company's efforts align with broader industry initiatives to create a greener and more sustainable technology ecosystem. On the business side, ASML is expanding its global partnerships and supply chains while navigating complex geopolitical landscapes. The company continues to adapt to evolving export controls, international trade dynamics, and national initiatives aimed at bolstering semiconductor self-sufficiency. ASML's leadership in technological innovation makes it a vital player in shaping policies and collaborations that influence the future of the global tech landscape. Looking ahead, ASML is also exploring emerging manufacturing paradigms such as photonic and nanoimprint lithography, which may complement or succeed current methods. These experimental approaches could revolutionize how chips are fabricated, enabling entirely new classes of devices and applications. Education and workforce development remain priorities as well. ASML invests in cultivating talent through partnerships with universities and technical institutes worldwide, ensuring a steady pipeline of skilled professionals equipped to advance semiconductor technology. The company's vision is clear: to empower the semiconductor industry to meet the challenges of tomorrow by continuously pushing the boundaries of lithography and related technologies. ASML's journey reflects a blend of deep scientific expertise, strategic foresight, and a commitment to collaboration that will sustain its leadership in an era defined by rapid change and innovation. As technology evolves and digital demands grow, ASML stands ready to enable the next generation of chips that will power everything from smart cities to personalized medicine, connecting the world in ways previously unimaginable. ASML's influence extends far beyond the realm of semiconductor manufacturing. Its technologies have become foundational to the modern digital economy and society at large. The chips produced using ASML's lithography machines power a vast array of devices and systems that shape how people live, work, and interact. The smartphone in nearly every pocket, the data centers that fuel cloud computing, and the automotive systems steering autonomous vehicles all rely on the tiny transistors etched by ASML's equipment. The company's machines enable innovation across industries including healthcare, telecommunications, entertainment, and finance, touching billions of lives daily. On an economic scale, ASML has become a key driver of growth in the semiconductor supply chain, which itself underpins some of the world's largest and fastest-growing markets. By providing the technology necessary to advance chip fabrication, ASML supports manufacturers in delivering faster, cheaper, and more energy-efficient devices. This progress fuels productivity, innovation, and competitiveness on a global scale. The company's economic footprint also includes employment and investment. ASML employs tens of thousands worldwide and has created thousands more jobs indirectly through its suppliers and partners. Its investment in research and development, often exceeding €1 billion annually, drives technological advancement not only within ASML but throughout the industry. Moreover, ASML's success has strategic implications for countries seeking technological sovereignty. Governments recognize that access to advanced semiconductor technology is crucial for national security, economic resilience, and technological leadership. ASML's machines are often central to government-funded initiatives aimed at bolstering domestic chip manufacturing capabilities, making the company a vital partner in national innovation strategies. Beyond economics and technology, ASML's impact touches social and environmental dimensions. The advancement of semiconductor technology has enabled breakthroughs in medicine, such as more powerful diagnostic tools and personalized treatments. It has also expanded access to information, education, and communication worldwide, helping bridge digital divides. Environmental sustainability remains an ongoing challenge and focus area. ASML is actively working to reduce the environmental impact of its manufacturing and operations, collaborating with customers to improve the sustainability of semiconductor production. The company supports initiatives aimed at minimizing resource consumption and waste, reflecting a commitment to responsible innovation. ASML's role in the global ecosystem exemplifies how a single company's technological leadership can ripple through society, influencing economic structures, geopolitical relations, and daily human experiences. Its journey underscores the interconnectedness of technology, policy, and social progress in the digital age. As the world becomes ever more reliant on advanced electronics, ASML's continued innovation and leadership will be critical in shaping a future where technology empowers people and economies sustainably and inclusively. The rise of ASML from a modest Dutch joint venture to a global technology powerhouse is a testament to vision, perseverance, and relentless innovation. In a world increasingly defined by digital transformation, ASML stands as a cornerstone of the semiconductor industry, enabling the creation of the chips that drive everything from everyday gadgets to cutting-edge technologies like artificial intelligence and quantum computing. ASML's journey is unique. Unlike traditional chip manufacturers, it doesn't produce the chips themselves but rather the extraordinarily complex machines that make chip fabrication possible. This niche, while highly specialized, has placed ASML at the center of a global ecosystem critical to modern life and economic development. The company's breakthroughs in lithography, particularly in extreme ultraviolet (EUV) technology, represent some of the most significant advancements in manufacturing science of the past decades. These innovations have not only extended Moore's law but also opened pathways to new computing paradigms and applications that were once unimaginable. ASML's role transcends technology. It navigates the intricate challenges of geopolitics, supply chain complexities, and market dynamics, all while maintaining a commitment to sustainability, collaboration, and excellence. Its partnerships with semiconductor manufacturers, governments, and research institutions highlight the interconnected nature of today's innovation landscape. Looking ahead, ASML faces a future filled with both opportunities and challenges. The demand for smaller, faster, and more energy-efficient chips continues to grow, driven by emerging technologies and societal needs. ASML's ongoing development of high-NA EUV systems and exploration of next-generation lithography methods position the company to lead the industry into new frontiers. Sustainability and responsible innovation will also shape ASML's path forward. As semiconductor manufacturing becomes more resource-intensive, the company's efforts to reduce environmental impact and promote circular economy principles will be crucial. Perhaps most importantly, ASML's legacy is about more than machines and technology. It is about enabling human progress. The chips produced using ASML's equipment power innovations in healthcare, communication, transportation, education, and countless other fields that enhance lives worldwide. In an era where technology's pace accelerates and the world becomes ever more connected, ASML's story reminds us that behind every breakthrough are visionary people, bold ideas, and the determination to turn the impossible into reality. ASML's machines may be hidden deep inside chip fabs, but their impact is visible everywhere, in the smartphones we hold, the cars we drive, and the future we imagine. The rise of ASML is, in many ways, the story of the digital age itself, a story still unfolding, with chapters yet to be written.